maze, scanning the black, tracking the heat, never turning back. Control 22, a covert gaze. Control 33, in the cosmic maze. Controls in the mix, secrets untold. Silent watchers, brave and bold. In the shadows, they silently glide, protecting our interest, far and wide. As fears, sentinel of the night, watching over with infrared sight, alerting us to threats afar, guiding our defenses like a guiding star. In the silence of space, they keep their post, shields unseen yet feared the most. With precision and speed, they warn of danger, keeping us safe from the missile's anger. As beers, sentinel of the night, watching over with infrared sight, alerting us to threats afar, guiding our defenses like a guiding star. And roles in the mix, secrets untold, silent watchers, brave and bold. In the shadows, they silently glide, protecting our interest, far and wide. As fears, sentinel of the night, watching over with infrared sight, alerting us to threats afar, guiding our defenses like a guiding star. As fears, sentinel of the night, watching over with infrared sight, alerting us.
Malaysian 370, contact Ho Chi Minh 120.9. Good night.
Good night, Malaysian 370.
Breaking news tonight, a Malaysia Airlines flight with 239 people on board, including 4 Americans, has gone missing.
From the Hindu scripture, the Bhagavad Gita. Vishnu is trying to persuade the prince that he should do his duty, and to impress him takes on his multi-armed form and says, "Now I am become death, the destroyer of worlds."
Hey everybody, welcome to the live stream. It is Science and Technology Thursday. I like how it works for Thursday and for Saturday because I am lazy. But yes, guys, I am back. Thank you guys for being in here, especially everybody who was in here early. I appreciate you guys. So today we're going to get right into some science. I decided we would hold off on the free energy plasma talk till tomorrow. I have a lot regarding the science around the plasmas, going way back, but also connecting Ken Shoulders potentially to Salvatore Pais, and I want to talk about that tomorrow. Tonight, we're going to talk about Julian Schwinger. And before we get into that, what I want to say, somebody asked what SIBRS is. SIBRS is space-based infrared system. Okay, space-based infrared system. Somebody also mentioned Brian Cox. I did watch part of the Brian Cox interview with Joe Rogan. It's crazy because he's one of the physicists that I watched on all those shows growing up and learned so much about relativity from. But it's just time for a new generation that looks at the universe in a slightly different way. 0-point energy. And we're going to talk a lot about that as well. Let me think. Where are we going to start here? Okay, so first thing I want to do is we're going to watch this video by Julian Schwinger because actually there are videos with Julian Schwinger in them. And Julian Schwinger explains relativity, special relativity, and optics. So it's a very interesting video, and we're going to talk about that a little bit. Before we do that, unification in general. I think the answer is there's been a lot of people that have figured out unification. So the big issue with physics and unification right now isn't that it's not been solved, but it's already been solved. It's just not recognized. And so now you've got like 8 different people that have like claimed to have solved it, and maybe even more, honestly. And they're all looking at it a very similar way. So, for example, people ask me about Nassim. I feel awkward. Can't remember his last name, but Harman, right? Yeah, Nassim Harman. He's got it figured out too. And there's only like small differences between how people are looking at it. Basically, everybody's figured out that there's an ether of energy out there, this sea of energy that's out there, and that we're kind of bathed in it, and that explains relativity, and it does that without having space be an empty void. And so that's like the next level of taking this science. And Julian Schwinger, this is where we're going to take a quick look at what he was known for. Because whatever it takes, like, I don't care if I have to learn quantum mechanics, electrical engineering, the history of all scientists ever, solve the UFO disclosure thing, whatever it takes, we're going to get MH370 solved, chat. No matter what it takes. That's why I'm wearing the shirt today, because no matter what it takes, you've got to deal with all that other stuff. We got to unify all physics. We got to figure out if aliens are real. Then whatever it takes, we're just going to admit MH370 got warped away by 3 orbs from the United States government, and then I'll call it a day after that. We'll rest after that. Here we go. Let me share this thing, because I started digging into Julian Schwinger and being like, okay, who is this guy? Like, what was his actual contribution? I knew he was a famous physicist, but like, we knew he had invented the Schwinger limit. Julian Schwinger was a prominent American theoretical physicist who made significant contributions to quantum field theory, quantum electrodynamics, QED, and other areas of physics. Here's a summary of his works. Schwinger's most renowned work was in the development of quantum electrodynamics. He's the guy that basically invented quantum electricity, like looking at the quantum world in an electric sense. And in terms of waves as well, and not anyway, for which he shared the Nobel Prize with Richard Feynman and Sean Irito Tomonaga, Japanese guy. I can tell he's Japanese just based on his name. He developed the formulation of QED known as Schwinger's action principle, which uses a perturbative approach to solve quantum field equations, which I think is significant because if you're thinking about perturbations through the ether, that's how we've been thinking about longitudinal waves. And what you guys need to realize, if you're new or if you are been here for a while, is that physics uses a lot of different terms to say the same thing, because it's their way of looking at our reality. But at the end of the day, everybody agrees the math works out a certain way. And that's what I think is changing. We're not reinventing all of physics, but we're looking at it through another slightly different lens where like there's this medium that's out there. Yeah, Feynman, I'm in love with Feynman. I'm in love with Julian Schwinger. Just these are my spirit animals when it comes to physics. Okay, unlike other physicists who directly dealt with fields, Schwinger developed a theory where particles and their interactions are described without explicit references to the fields. This approach, known as source theory, aimed to derive quantum theories directly from observable quantities. Now, why do I love this? Because he's using real observable information to determine what his belief system is about physics and how the universe operates. We're not going based on theory and math. We're like actually looking at it, and then we'll figure out how the math works out. And it turns out, oh, okay, math fits in. Hello, K-Stack, and everybody else who's jumped in. We're doing a little quick biography on Julian Schwinger. So he believed in observational physics, science. He introduced powerful mathematical techniques like the use of Green's function in quantum field theory, which are essential for calculating scattering amplitudes and particle interactions. So he went real deep on the quantum physics in terms of like what's happening with our wave functions at the smallest scales. Magnetic monopoles. This is when I got really excited. Julian Schwinger, known for one of the first people to seriously consider the theoretical implications of a magnetic monopole. Hypothetical particles that would be the magnetic counterpart of the electric charges. So like you could create like a bubble of magnetic field energy. Casimir effect. Although Hendrik Casimir first proposed it, Schwinger provided the significant theoretical work explaining the Casimir effect, where quantum fluctuations lead to an attractive force between two closed space conductive plates. You can think of it as mirrors if you want. He also contributed understandings of synchrotron radiation, which I had never heard of, which is emitted by charged particles moving relativistically through a magnetic field. So energy is what that sounds like to me. Nuclear physics. His early work included contributions to nuclear physics, particularly in understanding the magnetic moments of the neutron and the proton. He worked on extending quantum mechanics to relativistic effects, which is crucial for high energy physics. And this is what we're going to look at a little bit here. Okay. Let me see here. I thought I had another search, but I don't. Okay. Let's take a look at the video. Let's try not to get copyright striked here, chat. See the particles yet, not the eye floaters. No, I don't. I think the point is you can't see them. So, yeah, here's another question on Brian Cox. It was so weird, like discussing the ether without discussing it. Yeah, because the mainstream physics are trying to slow. What they're trying to do is this: like they have this view that space is empty, and so they're trying to work around to get to the idea of the ether, but working within a paradigm that doesn't let them get there, obviously. And then the problem too is that the way they're trying to do it, they're trying to say that it's quantum gravity. Is this quantum idea of quantum gravity? Gravity is happening in these quantum scales, which yes, that's correct, but if you don't understand it from the 0 point energy, that it's an induced effect from 0 point energy then just explains everything, like everything. Dark matter, dark energy, explains where energy comes from, how the lights are shining, like solves all the problems. Mass, inertia, gravity, everything. Everything solves. Negative energy is another way to look at it, guys. So the ways we should think and talk about it is like you want to talk to people on a basic level that like negative energy is real. And it's not the spooky energy. Everybody makes the joke, oh, spooky and negative energy. No, like negative energy is like how the light's operating right here. Like it's just pulling energy out of the ether. So Julian Schwinger realized that we could actually interact with this equilibrium of energy that we're sitting in. He realized that we could. I don't know if he's the first person to realize it, but he realized that we could interact with it with electromagnetic fields. So the Schwinger limit is the limit in which we're just yanking real photons out of the ether in the form of light. Light's getting pulled out of the ether. I think there's a direct connection here between negative energy as well and cold fusion, which is something that we're going to talk a lot more about tomorrow, which is that we don't need to jam the stuff together physically. We don't have to push. We can actually just warp space-time, and then the objects are just going to collide naturally. Just collide naturally. And that's what I think the Casimir effect is all about, and the dynamic Casimir effect as well. I thought I had something that talked about dynamic Casimir effect. But I want to go and show this too. Because it feels like when I read these posts about Schwinger, I feel like he would have been on board with the 0 point energy idea. It won't surprise me to find that he said something about like agreeing with it in general as well. The second question was from King Milkfart. Unbelievable. Wow. Yeah, there's something weird going on with those guys. My UFO community people. I really just don't care about the UFO community though, chat. I mean, I care about the few people that are cool, but a lot of them are just super weird. Nobel Prize winner Julian Schwinger of the Schwinger limit, in effect, studied under Oppenheimer Oppenheimer is in like the Manhattan Project, like Cillian Murphy was just playing him in a movie like last year. That's who Julian Schwinger was studying under. And he worked with Freeman Dyson. Freeman Dyson, I think, was famous also for working on atomic bomb or nuclear energy. Schwinger became interested in cold fusion in 1989. So what we're going to find out about tomorrow, guys, when we dig into the cold fusion stuff, is that 1989 was when Pons and Fleischmann reported that they could produce cold fusion at room temperature, that they had fusion happening at room temperature. It was producing excess heat in terms of like the coefficient of performance. They were getting much more energy out in the form of heat than was being put in, and it was producing fusion. Elements were changing. This is the same time where Schwinger, near the end of his life, got interested in cold fusion and started trying to publish papers. Schwinger felt that cold fusion was being suppressed from the public. He accurately predicted the death of science by corrupt academics. This was my real troll sentence that I threw in there, chat. So I'll read part of this here. While he was working at MIT, he was asked to participate in the Manhattan Project with Feynman, but chose to stay at MIT. So Julian Schwinger turned down a chance to work on the Manhattan Project. Can you believe that? That's huge. Maybe we shouldn't disclose this to the world. This feels like the only reason why I imagine you would do this is like, I don't want to make weapons, right? If somebody comes to ask you, hey, will you come make some doomsday weapons with me? Like, people are going to turn it down. They just don't want to be involved in it. After Feynman's death, he became interested in non-mainstream research of low-energy nuclear reactions, cold fusion. He wrote a theory about it. He resigned from the American Physical Society after the refusal to publish his papers. What? Guys, you realize the American Physical Society is like probably the number one like physics community, academic physics community out there, American Physical Society. This is where the LK99 thing happened just earlier this year in like March. They refused to publish his papers on cold fusion. He felt that cold fusion was being suppressed and his academic freedom violated. He wrote, "The pressure for conformity is enormous. I've experienced it in the editor's rejection of submitted papers based on venomous criticism of anonymous reveries. The replacement of impartial reviewing by censorship will be the death of science." Because what happened, guys? Everybody went all in on Einstein's relativity. They were all in on it. They had been teaching everybody Einstein's relativity is the be-all, end-all. And let's be honest, E equals mc squared is extremely important. It's so important. Why is E equals mc squared important, chat? Because it means mass and energy are interchangeable. We can convert energy into matter and matter into energy. And this means that if we create a field strong enough on our side, we should be able to pull energy out of this ether, out of this source. I think I misspoke a little bit there, because I think what he says in this video too is that we want to know what the exchange rate is when we have to change. And potentially we can manipulate that exchange rate. So the problem with cold fusion then was that everybody assumed it violated the laws of physics. They thought that it must violate laws of conservation of energy or the laws of thermodynamics. Now, Eli Prigogine wrote that we can achieve, if we achieve these states of extreme, if we pull out of equilibrium our energies, pull them out of equilibrium and make it very, very powerful, then we can have disorder turn into order. So imagine like you make a shape on the side of the beach, and then it gets hit by the waves. You make a castle, and you get hit by the waves, and your castle gets wiped out. Okay, so you're on the beach. You made your sandcastle, gets wiped out by the waves. When we go from disorder to order, it's like the sandcastle rebuilds itself just naturally. Like that's negative entropy. Like we're going backwards from what happened. And Prigogine basically suggested that this would be possible. Now, this relates to the Schwinger limit because the Schwinger limit is when space-time becomes highly nonlinearized. And Schwinger proposed that this meant that we pull photons. Particle-antiparticle pairs get pulled out. They're constantly being created, but this just yanks them out. So we would potentially see a flash of photons. And this is why I think it's so interesting when you look at it from the perspective of the MH370 videos, which is what we're seeing there. We're seeing a release of photons. So real quick, I'm going to show that just because I brought it up, and then we're going to watch this video. Fast forward this. I just want to go to the part where the plane flashes here. Should get a shortcut to this. There it is. So you can see this illumination actually accurately illuminates the clouds in 3 dimensions, which is really all you should need to know that this is real. Nobody's faking 3-dimensional accurate lighting on a hoax video. Certainly not one that's made to look like military footage. So this is a release of photons that you're seeing here, but also it's potentially very cold. So there could be ice flying off of this thing because we're seeing this extremely cold absorption of energy happen. This is potentially the first time that we've had large-scale proof of the Schwinger limit. Is that what's happening with those orbs is that they are able to create a charge density so high that it breaks through the Schwinger limit. This is what Salvatore Pais was saying. This is why it's so important to understand that there's a limit to our reality before you break into the ether. And it's an obtainable amount. We're looking at it right there. And it might be that we have to use plasma in order to pull it off. Like maybe we have to. Like that's just a requirement. Like that's part of the recipe. But that right there, I think, is the proof of the Schwinger limit. The fact that the photons are being released exactly as the theory would predict. And then as the orbs are converging, the Coulomb's force is increasing. They're creating a Casimir shell. It could also just be annihilation. I really can't rule annihilation out. But other people claim to have saw the plane later, so it feels like it's got to be teleportation. Okay. So it's crazy, though, because Julian Schwinger, and we're going to go to the next video here. His theories are very closely tied to dynamic Casimir effect and to interacting with the ether in general. He didn't just look at it as this impossible thing to interact with. He looked at it in terms of like, there's a field here. There's something here that we can interact with. Okay, let's try not to get copyright striked here on this. Okay, so this is a video that I found. It's actually Julian Schwinger explaining relativity. So if you're wondering, oh, why is this not exactly like, talking about the Schwinger limit? Because I found actually Julian Schwinger. This is really him. This is really him. We found a video with really Julian Schwinger going to teach us Einstein's relativity from his perspective. This is the best thing possible. I want to know, how is this guy thinking? That's what I want to know. So it's only like 25 minutes long. I'm going to play it a little bit fast.
For the third level course, Understanding Space and Time. It deals with the equivalence of mass and energy and some of the other revolutionary consequences of special relativity.
So when you guys are like learning in real time, like this is an actual like course by Julian Schwinger. Like this would basically be like one of his lectures. So, we're learning from the greats here. And what seems to have happened is that there was like a branching of different ideas from really Newton, but also on general relativity and quantum mechanics. And one of those routes, general relativity, specifically special relativity, they got the most attention. Everybody said that's got to be what it is. But there's always been other views. The ether idea has always been out there. In fact, I would argue more of the historical scientists believed in the ether than not. It's only now, recently, from the 1970s onward, more people think that space is an empty vacuum, which is kind of crazy to me. So we're going to learn here about waves, and there's some pretty cool visuals here. So if you're not strong on general relativity, this is going to be very important because you want to know, why is magic possible? Actually, a lot of people are like, the world we live in isn't that special. But what I'm about to show you here with Julian Schwinger is it is that special. Even in the world that the mainstream people agree upon, when it comes to space-time, it gets very weird. We can actually make magic tricks and illusion happen just through manipulation of space-time. And when we take that to its extreme, bend it around, we can actually create pure magic in terms of just Harry Potter. Go to here to here. Make a fountain of energy just shoot out. Like, we can actually interact with the ether in that way. And that view of physics in the universe is threatening, because not only does it really wash over a lot of what people have focused on for their whole careers, but it's a threat to governance. If you're not dependent upon anybody else, like, why do I need to be beholden to a government if I have any resource I need at my fingertips? You don't, really. And that can't be allowed either. It would upend our way of living. We would be in a situation where we would not have to want for anything, because we would potentially have unlimited energy at our disposal. But it potentially would lead to the end of the universe as well, because we might be able to create a big bang or a black hole or, anything. And really, anybody could create something powerful enough to destroy the planet. But on the other side, we could disappear. We could go to Mars or wherever, send Elon to Mars. I'm going to go to like the Andromeda Galaxy and hang out with Ambassador Bijou from the Andromeda Galaxy. They have a supreme ambassador just for their whole galaxy, apparently. And sometimes he hangs out with us. Okay, here we go.
We know that the absolute time of Newton has been displaced by the relativity of time. Physical processes take place more slowly when the system being observed is in relative motion. Moving clocks beat more slowly. Let's see where this leads us. We'll start with the light clock, which works by bouncing light pulses between reflecting walls. When the clock is stationary, a pulse of light moves back and forth in a certain time. But when the clock is set in motion with speed v, the light traverses a longer path and takes a longer time for one tick, one period of the clock. The increase in time is given by the factor gamma. Now we're going to use these same reflecting walls to draw some other interesting consequences of special relativity. This time we take two vertical walls, and we imagine a light source sending out pulses from the center toward the walls. Since they have equal distances to travel, the pulses reach the walls at the same time and return to the center also at the same time. Now let's imagine a similar setup as a kind of signaling system inside a spaceship, so that the light reaching the walls this time is picked up.
Okay, so we're flying around in a spaceship and we got light beams beaming both directions. Now, why is this going to be important? Is basically we're trying to figure out if there is an equilibrium state, or when we look at these objects while they're in motion and we're also in motion, or it's in motion, then how is the light interacting? How's the light interacting? Because this can create situations where we can really mess with conservation of momentum, or maintain it, and then it changes our perspective of how things look, to the point where it looks like things are bending and changing shape.
A large space station is nearby observing everything. Relative to the observing station, the signaling spaceship is in uniform motion. How will the light pulses be observed to travel? Now the left wall advances to meet the light pulse, while the right wall retreats. So to the observer in constant motion relative to the spacecraft, the consequence of light traveling at its invariable speed is that the two light pulses hit their respective walls at different times, the left-hand event here occurring earlier. If the spaceship were moving in the opposite direction, it would, of course, be the right-hand pulse that would arrive first. But notice, as before, that the light pulses always travel at constant speed c. Depending upon the relative motion of the observer, then, these events occur at the same time or at different times in either order. All right, but now let's change the signaling system.
So when it's moving, now the light, because the light's always traveling at a constant speed through the medium, then if that object is moving, then the beams of light are going to hit the walls at slightly different times. Now, that's exaggerated what we see in this video, but it's true. That's what's happening. And what that's going to do is, from somebody who's an outside perspective observer, it's going to look unusual. It's going to look weird. We're manipulating time at that point.
Let mirrors be installed at the ends of the ship so that the light pulses are reflected back to the center of the spacecraft. How will this new signaling system operate when observed from the passing space station? So the time situation will be reversed on the return trip, and the two light pulses return to the center at the same time, simultaneously.
That's pretty weird, right? Like, that's so what's going on here is that if you put a mirror now at each end, now they get back in sync. So even though it's traveling this way, they're still going to get in sync because each one is doing one half of each effect. So even though now it's moving away or towards you, or across your distance there, they're still going to be back in sync when they hit after they hit the mirror and get back. So you've now put them back into phase. Just simply by adding a mirror. That's all we had to do to balance out special relativity.
Simultaneous events at the same point in space are simultaneous for all observers in uniform relative motion. The two events at different spatial points that are simultaneous for one observer are not simultaneous for another observer in constant relative motion. Does that mean that a simple act like this could appear to another observer as the ball landing in my hand before I drop it? No. The reason is that there is a physical object in motion throughout this act, and any observer at whatever relative speed will be able to follow it and has no choice but to agree on the same sequence of cause and effect. This situation did not apply in the case of the spaceship, as the two light pulses had no cause and effect relation. The absoluteness of the speed of light, in the sense that no material object can ever attain it, was fundamental to the conclusions we have just drawn. But one thing we have not asked is this: what mechanical property prevents that limit from being attained? What is it in the nature of matter that makes the speed of light inaccessible? One way to investigate this question is with atomic particles, and in doing so, we shall be led on to further implications of special relativity.
So I already like what he's talking about here, because Julian Schwinger is basically talking about how do we break the system. This is the one thing that I talk about with the magic card deck. I say, when we're dealing with magic cards, I don't want a plain Jane vampire deck. I want the deck that's like destroying your lands, making you cry, run home to mommy, Ashton beat me in magic cards again. Wah, wah. That's the deck that I want. Everyone's cheating. You can't use that deck. That's what we're trying to do in physics as well. Is we're trying to break physics to the degree where we can manipulate these effects that we're seeing and ramp them up. And so if we manipulate, our environment, and we bend it to the point where we can cause things to stretch and look weird, red shifted and blue shifted from us, then if we ramp that up, does that just create a hole between 2 points in space and time, a wormhole?
When protons are channeled down long vacuum chambers, very fine beams can be produced, and these can be manipulated with very great accuracy. Inside particle accelerators, like this one at the European Nuclear Research Organization near Geneva, bunches of protons are driven up to very great speeds by electric fields. These are cleverly timed to keep urging the protons ever faster. This proton synchrotron, as it's called, was built in the shape of a ring, about 200 meters across. It produces protons traveling within a fraction of a percent of the velocity of light.
So this dude was familiar with the first particle accelerator. This particle accelerator, I think, is the one before LHC. Just fact check me on that, chat. I'm just doing that from memory. But so they were using particle accelerators right away because they were trying to figure out. How we can manipulate the speed of light. If we can manipulate the speed of light, how inertia and mass balance with this speed limit. How is that possible? Let's find out.
In 1976, the protons from this ring were injected for the first time into a giant new ring of magnets, many times larger than the proton synchrotron. Buried beneath the soil, this super proton synchrotron measures more than 2 kilometers across and is one of the most powerful machines ever made.
You can basically buy this like particle accelerator like off the shelf now. Like that's how obsolete this is. Lasers just make all this stuff obsolete, chat. It's kind of sad. Like once you realize negative energy is possible, like a lot of the stuff we do is just stupid and obsolete. Like straight up caveman level stuff.
Once inside the SPS, the protons are again subjected to strong electric fields. These urge the protons on, so that eventually they end up with 40 times more energy than when they entered. But remember, the protons started in the SPS at almost the speed of light. So what happens to their speed as the energy goes up? Well, there's the energy going up. It goes up from 10 GeV up to 400, which was the factor of 40. But look at the velocity. It goes up in the first phase of the acceleration quite quickly to almost the speed of light, but then it just flattens off. How can we explain that? How can you push something along so that it gets more and more energy, but it doesn't go any faster? Well, it must mean that the inertia of that particle is going up. Its inertial mass. And we can show that, too, on this output. There in the center of the screen, you've now got the mass displayed. As you see, it's going up along with the energy. And that has to be the explanation of why it is that you can't push a proton or any other particle faster than the speed of light.
We are now going to give a precise form to the idea that mass, or inertia, increases with the speed of the body. We shall apply the concepts of special relativity and the conservation of momentum.
I can't remember if he goes to the thing here, so I'm just going to jump in. This fits perfectly in with 0-point energy, 100%. So what do they just try to do there? They try to use this outdated, stupid caveman particle accelerator, and then they wanted to charge up the electron, the particle, whatever, to try to push it past the speed of light. But no matter how hard they push, the thing just cuts off. Like very quickly, it hits maximum speed, and then it doesn't increase acceleration anymore. And so what they did is they found out is because the mass is increasing as well. So basically, this is why it's hitting the speed limit. Is as we increase the energy, the mass keeps going up as well, more and more and more. The faster that thing starts to go, and then it hits, just levels off. So in the 0-point energy model, the 0-point energy is the resistance. This is the reason why we push harder and harder and harder. We're pushing against the ether harder and harder and harder. Same exact concept. We're pushing against that energy that's out there. If it was an empty vacuum, we should just be able to keep pushing it to infinity. But we can't. We should look at it like we hit the ceiling. We hit the ceiling. So then the question is, how do we break through that ceiling? How do we break through that speed limit? That's what I think Julian Schwinger wondered when he was thinking about the idea of the dynamic Casimir effect and the Casimir effect and the Schwinger limit and the Schwinger effect of pulling these photons from this ether.
Let me start by reminding you of that conservation law with the aid of this simple toy. Clearly, all the momentum of one body is transferred to the other on impact. We can repeat it using effectively twice the mass. And the same thing happens. But now, let's use bodies of different masses. We can see that the heavier mass acquires a smaller speed. This becomes more interesting if we set both balls in motion. The momenta of both balls are being reversed on collision, and the heavier ball is clearly moving more slowly, just as demanded by the conservation of momentum. We are now going to combine these two ingredients of momentum.
That was not a good spot to pause, but so what did he just show with the balls hitting one another there? We had this, now we created a situation where the heavier ball doesn't bounce back as far because momentum has to be conserved. Remember, with negative mass, what happens? And negative mass and energy are interchangeable. That's what E equals mc squared should us. Energy and mass are interchangeable. So with negative mass or negative energy, when one of them comes near the other, it starts to chase it and it flies off. And if that happens, then now we've created a perpetual motion. We've got perpetual motion now, where as long as we can maintain this, we can create the force of gravity anywhere we want. We would fundamentally then, I guess, it doesn't necessarily break conservation, because if you add it together, F still equals ma, or A still equals F divided by M. We've just made M 0. Lou Elizondo's taking questions in X space. Can we listen to school him right now? I can't even join. No, I don't want to school Lou Elizondo, guys. I don't think he's a bad guy. I just think he's sold his soul to the machine. Sold his soul to the machine, chat. Let's just get real condescending on him. Lou Elizondo's he's not a bad guy, chat. He's not a bad guy. He's a good guy. He's trying to do right by his family by selling his soul to the devil, to the powers that be, to that, because they know better. Military knows better than the people. Nobody else will keep us safe, So sorry, you guys can't have any technology or free energy. You can't change our world because we are keeping you safe from yourself. So there you go. I honestly think that's how they think. So I mean, I don't really care, because I don't know. We're pushing disclosure further than he is. He did every single mainstream show, daily show, and all he did was talk about aliens. What did he get out of it? Nothing. How many more people believe in aliens than believed in aliens a month ago? Practically none. Let's just be generous. 5%. 5%. It's probably not that much, but 5% more people. Oh, great. Moved the needle. Sold a book and went on a 20 video tour, or 20 interview tour. You convinced 5% more people aliens exist. Great. Bravo. Wait, no, let me do a slow clap. Bravo. Or we could just give everybody free energy, because it's going to happen anyway, and just let the cards fall where they may. End of civilization, new economies, whatever. Just let it happen. What are we waiting for? Hold on. What are we waiting for? All of a sudden everybody to become all altruistic? Are we waiting for the WEF to maintain perfect control of this world? What are we waiting for? Let's just get it out there and see what happens. The world's a shithole place right now. It's not getting any better. It's only getting worse, if you ask me. So just give us the free energy shit. You give us the free energy, the balls of plasma, so I can have my own little Jarvis. Actually, I'm going to have 4 Jarvises. I'm going to have 4 for 4 orbs. 4 little Jarvises roaming around. And then they'll just teleport me wherever the fuck I want to go. Okay, we're getting spicy. Let's keep going.
Conservation and the concepts of special relativity in a kind of space game. A spaceship at rest is designed to fire a projectile broadside. Now, 2 spaceships at rest do the same thing, firing towards each other identical projectiles that move at equal speed. They collide and recoil along the line of fire. Let's concentrate just on the velocity of the projectiles before and after the collision. It's clear that the projectiles carry equal and opposite momenta. The total momentum is 0 before the collision. And it is also 0 after the collision. Momentum is conserved. No problem here, but that's not a very exciting game. So let's add another ingredient. Suppose we now move rapidly relative to one of the ships, or equivalently, one of the spaceships is moving rapidly relative to us. How do we perceive things? As you remember, lengths along the line of motion are contracted. All right, but how about the act of firing? You will also remember that time significantly slows down. So the act of firing the projectile from its mothership is slowed.
So it looks all squished, chat. That's why it's squished, because it's moving away from us, I think. I get kind of confused on this video.
As the spacecraft itself is moving, let's look at it again in a way to emphasize the transverse motion of the projectile.
I think it's coming at us now.
Well, so far there's nothing new. We have seen the conservation of momentum and the effects of special relativity. Now we combine them in a new game. Let the two spaceships move relatively to each other. Each of them fires its projectile.
Okay, fire their projectiles. Yeah, yeah, that looks interesting. Okay.
Let's look at that end on to concentrate on the transverse motion.
Constant transverse motion, chat. We're looking at head on. The first one's going to feel like it's shot first, but they both shot at the same time. See?
Clearly, momentum conservation still holds. How does the same collision look when we move with that spaceship A? That is, when A is at rest relative to us. Obviously, A fires broadside. B, being in rapid motion, exhibits all the time-slowing effects we have discussed. How does the whole incident look? There's something different there. B fires first. By changing frames, we've lost the simultaneity of firing. That's just what you would expect from our discussion before, but we want to concentrate on something different here.
So basically, Schwinger was like, okay, so you just shot two things at the same time, but now based on the perspective, it looks like the other one shot first, but just based on the perspective. So did we just warp time? How did we do that? People should really think about this more. This is a fundamental truth of our reality. And the answer is we're looking at light beaming through refracting through a medium, space-time. And everybody would say, well, nobody disagrees on that. Yes, but we're actually talking about it actually being a medium and not just empty space. And that is important because if there's a medium, there's energy there that can be extracted.
Let's look at it again from the end view.
So that first one shot first.
The transverse velocities of the two projectiles are different. Yet this is just another view of the collision where the two velocities were equal, where there is no doubt of.
So that's just, I think that one's if we're sitting on top of the rocket there. And you can see here now we've shifted what looks to be like we've violated conservation of momentum here. But no, we haven't because the mass is increased on the bottom one.
Momentum conservation. All that has changed is the frame of observation.
I guess I said that correctly.
So momentum should still be conserved. How do we reconcile this? The heavier ball is moving more slowly. There's the answer.
Oh, that was great. I didn't
is the frame of observation.
Watch this.
So momentum should still be conserved. How do we reconcile this?
So there's your answer right here. Hold on. Let me see if I can get it. Yeah. So you can see the distances. This is how we reconcile it. Is that the smaller one has less mass. It's bouncing away further. The fatter one doesn't bounce as way as far. So mass is what's balancing this out. So our answer to unifying physics must include an explanation for mass and inertia. We have to be able to explain this. And this is why F equals ma is so important. Force, or we're going to say it the right way. Acceleration equals force divided by mass. Because if we have negative energy, just following the math, just from what we've learned here today, E equals mc squared, which means mass and energy are interchangeable. And we're looking for negative mass. Well, what about negative energy? What if we don't care about negative mass? What if we just care about negative energy, since you said they're interchangeable? Oh, and it turns out we have something that is negative energy, the Casimir effect. It's just not what we expected. It's not a magical substance. It's just a negative pressure that we create by pulling out all the zero-point energy fields. Just like if we were dipping into the ocean, spreading it out, it's going to try to collapse back upon itself. This concept of this cavitation, I think they call it, this is extremely important in cold fusion tomorrow too. And this is what the people that figured out cold fusion figured out too, is that we can create these negative energy pressures without using a huge amount of energy. And this is just much more efficient than trying to do hot fusion and forcing stuff together. Like, just let nature do the work.
The heavier ball is moving more slowly. There's the answer. Very good. Here, as anticipated, is a mass that grows and grows as the speed approaches the speed of light. And the effect of that is to prevent the speed of light ever being attained by a material body. But that's not the end of the story. The gamma curve used V over C as the horizontal axis. It doesn't look very different if we change that axis to the square of V over C. But suppose we magnify the beginning of the curve for very small values of V over C, where gamma is slowly rising above unity. We get a straight line, and its slope is a half, or in symbols, gamma minus 1 equals a half V over C squared. So the mass at low speeds is given approximately by this. The combination of a half mv squared is the Newtonian expression for the kinetic energy, the energy of motion. And we see that an increase in energy of a half mv squared produces an increase in mass equal to 1 over c squared times that increase in energy. Or delta E is delta m c squared. Here is the relation usually presented as E equals mc squared that has become the hallmark of Einstein's theory of relativity.
Ta-da! That was a great magic trick he just did there. I love that. He basically just showed you this is how we get equals mc squared. This is how we're able to do it. We just explained why equals mc squared. Is that as our velocity is increasing towards the speed of light, the mass is also increasing equivalently. And then we can just do the math and we say as the energy changes, then the mass changes as well. The more energy we add, the more mass is going up. This is the equation. This is why equals mc squared. How crazy is that? It's really important to understand the history of where E equals mc squared came from, and we just learned it. Take a particle accelerator, try to increase the energy of the particle, and as you approach the speed of light, you can't go beyond it. Apply that to the math, and you get this. Change in energy equals change in mass, which means mass and energy are interchangeable. Wow. Bravo. Guys, if you're here and you just learned that, you probably already know more than most undergrad physicists and engineers do. Like, they just know the equations, but if you understand the concepts behind it, why it's so important, now we can understand how we can add on to physics. We understand where the barrier is. E equals mc squared. We can't deny this. We've seen the experimental proof of it. But does this limit us? What if we take this equation and we make mass 0? What if we approach 0? You know, these are the things where now, how do we break the equations? And this is where people have been able to prove that warp drives and wormholes are mathematical solutions to Einstein's equations, just like E equals mc squared, the solution of gravity and space-time. Negative mass. Yeah, negative mass means, and this is why Bondi in 1950s went in and showed that we can actually create negative mass. And it's a little bit of them being coy because we don't need to have mass. A lot of them will say in their papers, they say, throughout this paper, you can exchange the word mass with energy because they're interchangeable. Because it's hypothetically possible that negative energy can exist, but not negative mass. How? Because we're in the ocean of energy. All the energy below us that's there, but we don't actively perceive, is negative. But it doesn't form a mass. Technically, it might, but not on levels that we can perceive. And if we dip into that, we're dipping into the negative energy, but we're producing real energy, normal energy, which means that all mass is just normal mass, but you can still have negative energy. It's just a matter. And now all the math equations still work out. But now we've looked at the universe a different way. We've unlocked a reactionary force to gravity. A reactionary force to gravity. And that's what the Casimir effect also shows. And before we finish the stream or the video here, this is why I say we're not going to recreate all of science. That's not what this is. I'm just an investigator. What we've found as we've investigated and started with just a missing airplane is we found a whole branch of physics that explains what we see in 2 videos of the plane disappearing. And nobody really accepts this. Like, this is it's considered fringe physics. But what we found out is that academia is completely full of shit, and they have huge gaps in their understanding of physics, and they have no right to talk down to anybody else on their theories. And this theory happens to have videos that prove that it's real, and it happens coincidentally to explain every single gap in physics, every single one. Except for maybe some minor things that I'm unfamiliar with, but all the main gaps in physics are answered. That, I don't know, that physicist guy, I don't even remember what his name was. He's done a TED Talk or whatever before. I watched his TED Talk. So if you're, this is an inside thing if you're not familiar with the story, but I don't know, he was replying and we went back and forth a little bit, and someone found his TED Talk, watched his TED Talk, and it's basically physics doesn't know anything. Ha ha ha. We don't understand why the outside of galaxies spin at the same speed as the inside. It should spin slower. We don't understand what dark energy and dark matter is. We don't understand the stickiness that we see out there. And I'm going, yes, we do. And if you're a physicist, your whole point of being a physicist should be that you want to figure that out. Turns out 0 point energy is all out there. His whole thing is about talking about how much we don't know. I don't know anything. Grr. Like, oh my God. Well, then read some alternative theories. Come up with something. Figure something out. Do some experiments. I think just being someone like, we can't know stuff, and that's funny, ha ha ha, is like just absurd. What's the point?
Here is the relation usually presented as E equals mc squared that has become the hallmark of Einstein's theory of relativity. That mass in its totality can be converted to energy is a very strong statement indeed. It goes beyond the partial conversion of mass that fuels the sun and nuclear reactors. Well, in what kind of environment can we find direct evidence for it?
To look into this interchangeability of energy and mass, we come once again to CERN with its world of high speeds and big accelerators. Now, you remember I said that the superproton synchrotron accelerated the protons to very high energies. What happens to that energy?
Okay, I want to answer this question too, because this is a great logical deduction. If energy can do work, does negative energy undo work or backwards time? I call it negative time. But yes, theoretically, because really we're talking about entropy and we're talking about order and disorder. You know, things go from orderly to disorderly. That's the common belief. But can things go from disorderly to orderly? That's backwards time from our perspective. And what would that mean? Backwards time wouldn't mean that we're going to a past universe. Entropy for the rest of the universe is still going forward. But your localized entropy, if you could target a specific person or body part or tumor, you could undo the time and you could reverse the entropy process, potentially. What would that do to somebody? You guys can test it first.
Well,
but I think it could be infinite aging or reversing the aging process.
Particles are fed off from the SPS into a number of different detectors set up to study the way the protons behave. Inside this huge magnet is a detector called a bubble chamber. It's a device for taking pictures of subatomic tracks. This one contains some spectacular secrets of what can happen to a proton. In a bubble chamber, what happens is this. Particles from the accelerator are passed into the tank of liquid hydrogen. As each goes through, it slightly warms up the liquid along its path. A little while later, tiny bubbles of hydrogen gas form. These bubbles grow to be much larger than the particles that cause them. And once they have grown to a visible size, they can be photographed. And this gives us a permanent record of the particles' paths.
So is anybody else getting sonoluminescence vibes here? It's like we're using a bubble chamber and now we're putting hydrogen through it and now these bubbles are forming. And why? Because the bubbles creating this cavitation, this negative pressure zone where it's causing the elements to collapse upon themselves. I think this is what the Casimir effect is showing as well. And we don't have to use water to pull it off, but water seems to be a good substance to use for cold fusion.
When you realize that you're looking there at a record of a particle that is only a millionth the size of a pinhead, you'll appreciate the incredible ingenuity of the bubble chamber. Now, the paths of the particles, or as we call them, bubble chamber tracks, they're examined on a scan table like this one. It's here that the secrets of the particles are revealed. And the way it's done is that we examine these tracks and we measure them up.
Okay, so we're going to examine these tracks, blah, blah, blah. We're going to look at the interactions with the particles. Gerald says, if heat from a system is produced from entropy, then cold is produced from negative entropy. Exactly, guys. This is so important. This is so important because when we're watching the MH370 drone video, this is the secret sauce. This is negative energy that we're looking at because cold is being produced, not hot, cold. This is why it's not an implosion either. An implosion would also be a positive entropy event, even though it's an implosion. Even though it's collapsing on itself, that would be like hot fusion, basically, but it's still going to be hot. The fact that this is cold is alarming because there was not some zero-point energy physicist that faked this video. Right? This is the strongest evidence that the video is real. There's no such thing from a mainstream conventional point of view that this should be able to exist. This exposes cold fusion, this exposes negative energy, and that we can use that to produce a wormhole, which is probably the craziest part, frankly. I wish this just showed that negative energy was possible and there wasn't 239 people that got disappeared in that plane, because it'd be a lot easier to sell to people. But the fact that we committed this horrible, horrible, horrible atrocity to prove that negative energy is real, God, that's wild. Just wild, man. Okay. Let's go back to it. But it's like, who do people think faked this? People are like, oh, some bored kid faked this? Are you fucking kidding me? With accurate Coulomb's force physics here, perfect like triangle formation around the plane. I'm not sure computers could pull that off in 2014 to get the orientation around the plane perfect, and then to have this negative energy event. Some bored kid just was like, yeah, it's going to be this negative energy event we're going to create in a thermal video. And it's not like, it's not visual. So you can't even be like, oh, they just decided to make it black. Like, no, it's every color we see here is very specific, including the engines on the plane. Nobody faked this shit. This is just real. Okay, we're almost done.
Data is fed off into a computer, and from the characteristics of the track, that one is able to infer just exactly what that particle was doing as it was going through the liquid. Well, what does it do, apart from make a track? Well, most of the time, it does nothing. The atoms of the liquid are mostly empty space, a tiny nucleus, rich in hydrogen, a proton, surrounded by an even tinier electron. So the particle just coasts along and passes out the other end. Sometimes, however, the particle scores a direct hit on one of the protons. And then what usually happens is that the particle bounces away and sends the struck proton off in the opposite direction. This recoiling proton has enough energy of its own to create a track, and so we end up with two tracks instead of the original one. This is just such a photograph. You see the track of the incoming particle on the right and the two outgoing ones on the left. Well, that's just a simple collision, not very interesting, just to help us get used to the idea of looking at these bubble chamber tracks. But there's something very much more interesting on the next photograph, so let's bring it up. But this time we've got four tracks. Well, two of the tracks obviously correspond to the incoming particle and the recoiling proton. But what are the two extra ones? Well, they have to be caused by particles of some kind, and they would be particles that were not present before the collision. So where do they come from?
Somebody says that wave conjugation. I would say you're starting to see it now in terms of like, this is why waves are so important. Because why we shouldn't just jam things randomly together. If I just start throwing rocks at some other rocks, some of the rocks are going to hit each other, but most of them are not going to hit each other. What we want to do is we want to focus the beams so that we can actually focus the things that literally collide with one another on the smallest possible zone and create the highest possible energy densities. How do we do that? wave conjugation, phase conjugation. You want to get all your waves in phase, lined up on one another. And light is a boson, which means it collapses down on itself. So we can have our light collapse down onto a single point and we get double the energy out of it. So yes, we want to have our phase, we want to have wave conjugation. This is where at the quantum level, like cymatics is very important, because what we're realizing at certain frequencies, there is literally coherence we see get formed. Order gets formed from chaos. We can see it. Pattern gets formed. And so that's where, like, those are the types of things that if we're trying to break through reality, that's what we're turning it up to 11. We're using the cheat magic deck. Those are the things we want to be looking into. Superconductivity as well. Superconductivity is when the current just never stops flowing because there's no resistance. They never hit anything in that scenario. And superfluidity is with the it never stops moving.
Well, when measurements are carried out on these tracks, it turns out that the energy carried by the 4 final particles is less than the energy of the incoming particle. We can arrive at this conclusion by the characteristics of their tracks. Remember I said that there was a magnetic field on the bubble chamber? Well, the purpose of that is to curve the tracks, and the amount of curvature depends upon the electric charge carried by the particle and its momentum. And from its momentum, we can get its energy. As I say, when you do this calculation, it turns out that you end up with less energy of motion after the collision than you had to begin with, that was brought in by the original particle. So, energy missing and 2 new particles created. Well, you've guessed it. What's happened is that some of that original energy of motion brought in by the particle in the accelerator has been transformed into the matter of the 2 new particles. It's an example of the interchangeability of energy and matter.
Booyah. So, okay, if you didn't understand that, when the 2 particles collided, boom, they created 2 more particles. 4 particles came out. And so we added up all that momentum and we realized there was some missing. So the answer is obvious. We lost some of the energy because we created 2 new particles. 2 new particles got created. So this shows that we can actually convert matter into energy. Very important if we are creating an atomic bomb to wipe people out. Now, the other aspect of it, this isn't anything that's even controversial. This is all just standard physics that we're talking about here. If we can produce negative energy, and we can basically just get free energy. And now we don't even need matter. We don't need mass in the equation. We don't even need we don't need this thing anymore. We can just have anything. We can just pull energy out anywhere we want. And that's where we can really just start to do Harry Potter magic with it. Because now we can break physics. We can create our magic card deck that's going to bust everything.
We have an even more convincing demonstration of that on the next photograph.
Actually, I want to say this too because this is good. Like I pulled the clip of Carl Nell. In fact, can I play it? I might have it. Why is this important? Because this is Carl Nell here. He was a
point is faster than light.
He was a 13-year deputy CTO, chief technology officer for Northrop Grumman. 13 years. And he's in the military too, so you know he's going to be a straight up guy. 13 years, direct deputy chief technology officer for Northrop Grumman. Let's see what he has to say.
The second point is faster than light travel. Everybody says faster than light travel is not possible. This is false. Miguel Alcubierre, a postgraduate student at the University of Mexico in 1994, solved Einstein's equations for an effective faster than light mechanism. NASA has investigated this. Everyone accepts his solution as valid. His solution requires negative energy. In 1960, quantum physics demonstrated or predicted the reality of negative energy. In the 90s, the Casimir effect was demonstrated in the laboratory. The Casimir effect demonstrates negative energy. The expansion of the universe, which is caused by dark energy, is negative energy. So we have a solution to Einstein's equations that allow effective faster than light travel. We've got the existence of negative energy proven. This isn't an engineering solution. This isn't a means where we can go and do this, but theoretically it's possible.
I mean, chat, what more do I have to say, man? Carl Nell just said what I've been harping on for the last year. Like, bingo, exactly. Could Carl Nell have sent the letter to Ashton Forbes? This is where you start to realize, guys, like, it's all just real. It's all just real. You don't have like General Flynn being asked about crazy technology and dudes who are 13-year deputy CTOs of major defense contractors openly talking like this unless there's something to it. There's not some major disinformation campaign to like get us to believe that gravity manipulation is possible. It must be possible. All forces can be manipulated. It's not that crazy of a thought. So negative energy is possible. Faster than light travel is possible. They literally accept that warp drive is possible. They just say, well, it needs negative energy, so we're not going to believe that. But like, yes, you prove that Einstein's equations show that we can create warp drive. Prove it. Crazy. What was he saying there in the middle?
In 1960, quantum physics.
Oh, yeah. So he was talking about Bondi here. Bondi, I thought it was 1951 or so, maybe 1959. I can't remember the year. But Bondi was the first physicist to come and say, no, negative energy, negative mass is possible. And that's why it was so important when we were just watching a second ago, Julian Schwinger, because he's saying, look, energy and mass are interchangeable. This should make us look at the situation completely differently, because there can be energy at this quantum level. And that energy at the quantum level can explain the stuff that we don't understand, because we can just look at it as negative energy. That means that we're in an equilibrium. We're not sitting in an empty jar, or our jar's fishbowl is full.
Well, straight away you'll see that it's a much more complicated picture than the previous one, so we'll have to take this in steps. Once again, the particle comes in from the right. As it collides with one of the protons in the liquid, it produces 1, 2, 3, 4, 5, 6 tracks. In other words, 4 new particles. But having said that, you'll notice that we haven't yet accounted for all the tracks on the picture. And the reason is that, as well as the production of 4 new particles, a pulse of light is also created. You can't see it on the photograph because light does not leave a track in the bubble chamber. But in point of fact, the light crosses over to there and transforms itself into 2 new particles. One is an electron, and the other is a positively charged electron called a positron. Now, this is an example of the transformation of pure energy, pure electromagnetic energy of the light pulse into matter. Right now, what happens to these 2 new electrons? Well, the negatively charged one goes spiraling off into the distance, gradually losing energy to the liquid, until eventually the electron stops. But meanwhile, what's happening to the positron? Well, it starts off in its characteristic spiral, but then it hits one of the atomic electrons belonging to the liquid and transforms back into light. So that's the kind of thing that happens here with the bubble chamber technique.
So he's pretty much just explaining sonoluminescence right there, chat. I mean, it's like, look, you create these particles and a flash of light gets pulled out of it. This is the dynamic Casimir effect, the Schwinger limit. The Schwinger effect as well is basically the dynamic Casimir effect. That you reach a point where you break the nonlinearity, or you break down and form a nonlinear space-time through breaking the Schwinger limit, and now photons are just getting poured out. Imagine like we can make a well where we're just tapped into the ether and we're pulling light energy straight out of the ether. Then it's just an engineering problem of, okay, how do you get it in an electrical form? We have free energy. Free energy. I was also looking into some metamaterials earlier today that are basically able to slow light down, and this can retard the dipole collapse. So you can keep your dipole open for longer using the right metamaterials. So now you can have a situation where there's free energy too. You can get free energy multiple ways. They're just massive efficiency. You're like, okay, your dipole just is like closes. It's like 99% more efficient. Just stays open 99% more. You're like, yep. Yeah, so this is a charge pump, apparently is what it's called. I didn't even know what it's called. But yeah, basically you can just manipulate the efficiency of the capacitance, and now you could probably get just free energy that way too. That's how crazy it is. There's more than one way to get free energy. There's like several ways to pull it off. It's all just based on understanding that there's this reservoir of energy you can tap into. It's crazy we haven't figured it out collectively yet.
And with other techniques, we can investigate this interchangeability of matter and energy. And all these interchanges are taking place according to Einstein's equation E equals mc squared. Right, well, there's one final point that I want to make, and that concerns the exchange rate. How much energy is required to produce a certain amount of matter, and vice versa? Well, I can illustrate that in the following way. Suppose that coin were made from positrons, and this one is from ordinary electrons. Suppose we brought the positrons and the electrons together so that they could annihilate in the way that we've been seeing in the bubble chamber picture. How much energy would we get out of that? Well, the answer is the equivalent of 40,000 barrels of oil, which is pretty staggering. And that, in fact, explains the enormous power that we get from nuclear power stations and from nuclear bombs. Those are processes which give rise to very efficient changing of matter into energy. It also explains why CERN requires those enormous accelerators to produce even these tiny bits of matter on these photographs.
So that is the presentation by Julian Schwinger. If you guys find any other videos on Julian Schwinger, please put them in the Discord. I am curious on if he has other videos, especially anything on the Schwinger effect and Schwinger limit that he's talking about. That would be amazing. I did not realize there was even videos from Julian Schwinger available on the internet. Hopefully, there's Discord right there, guys. Hopefully, you guys learned a little bit more about physics tonight in terms of general relativity, special relativity, and how we can kind of warp our perception of events based on relative movement and relative perspectives. And then the idea of how do we break our reality? How do we break it? And we know there's something there because when we look at the interactions, experimental interactions, and when we collide particles together, we're seeing energy come off in the form of light, and we're seeing other particles getting created, almost like you're fracturing one particle into pieces. So we know there's something to interact with. The only thing at the end is that if there's a way where we can actually minimize the energy the energy usage to cause these events to happen, then we can get massive returns. And then we can also just cheat on the engineering perspective, like I think Gerald was just talking about in terms of the capacitor pump, and potentially amplify energy in the circuit itself. So multiple ways to skin this cat, as so many have said. I think that's everything that I wanted to go over tonight. Sorry, it's going to be a short stream tonight, guys, because I'm wiped out from traveling all week. I was at work all week doing my normal job. That's why there wasn't any videos getting posted. Did my best on that. Please check out the interview with that I did earlier this morning, or that I think got posted earlier this morning, maybe yesterday, with Curious Crossroads chat. I'll put a link in the chat. Watch the interview with Curious Crossroads. Hopefully this link works. I did one in person. They were actually out here in Minnesota, so went out, drove out to them, did an interview. I think it was really good. Spoke about the physics, the science, some of MH370 stuff, whatever they wanted to ask. They asked me about aliens and Dr. Greer, stuff like that. So check this link out, guys. Thank you for the happy birthdays. Appreciate it. I don't really care about birthdays, but whatever. So tomorrow the plan is we're going to talk about cold fusion. Might start a little bit late tomorrow, 7:30-ish Central Time. But it might be on time at 7 o'clock. I've got a bunch of stuff to go through. Found a deep dive on cold fusion, found a video explaining the suppression of cold fusion and how similar it is to LK99, Ken Shoulders, Sal Paez, Hal Puthoff, all these guys are connected to it. Like, we just watched Julian Schwinger explain this idea of cavitation and nuclear collapse. So look forward to that tomorrow, guys. Anyway, have a great night, everybody. I'll see you guys tomorrow. Go Vikings. Skol, baby.
In the fields where the skies are wide, talking about a journey through the cosmic ride. Einstein and Thorne, they set the stage for a trip through time across the space age. Wormholes connect distant points in space, traversable paths to a far-off place. No black holes pull, no crushing weight, just a cosmic tunnel to a distant gate.
Talking wormholes, stargates, negative energy, travel through the cosmos, it's our destiny. MH370, where did it go? Bowling 777 through a wormhole flow. We're talking wormholes, stargates, negative energy, travel through the cosmos, it's our destiny. MH370, where did it go? Bowling 777 through a wormhole flow.
Exotic matter, negative energy's the key to stabilize the wormhole for you and me. Quantum vacuum squeeze so tight, creating conditions for this wondrous flight. Static fields and lasers in the lab they play, generating forces in a new kind of way. Gravitational squeezing, Casimir's force, negative zones we need to stay the course.
Talking wormholes, stargates, negative energy, travel through the cosmos, it's our destiny. MH370, where did it go? Boeing 777 through a wormhole flow.
Thin shell formalism plates so fine, spherical geometry we realign, energy conditions that we must defy. For a stable wormhole, let's give it a try. Forces balancing the plate, creating the throat, open the gates, from Earth to the stars in a single bound, a shortcut through space profound. Engineers and dreamers hold the key to future worlds and what we could be. With science in hand, we forge ahead through the cosmic paths that we now tread.
We're talking wormholes, stargates, negative energy, travel through the cosmos, it's our destiny. MH370, where did it go? Boeing 777 through a wormhole flow.
From the fields to the stars, we break the chains. Understanding the universe, we make the gains. Lil Hula Crunk shines, bringing truth to light. Through his music, we'll explore the night. With wormholes and stargates, our path is